For more than 300 years, some of the smartest people on the planet have been wrestling with a really weird question. What exactly is light? And trust me, the answer takes us on a journey with twists and turns that seriously make you question the nature of reality itself. Okay, so let's get right into it. The whole massive, centuries-long debate really just boils down to this one question. Is light a continuous wave, kind of like ripples spreading out in a pond, or is it a stream of tiny individual particles, like a spray of sand? Well, as we're about to see, the answer isn't a simple either or, not even close. So, our story starts way back in the 17th century with an absolute giant of science, Isaac Newton. He pointed his incredible brain at this puzzle of light and came up with an idea that, honestly, just seemed to make perfect sense. Newton's idea was that light is made of these teeny tiny hard particles he called corpuscles. And, why not? It explained a lot of what we see every day. Light travels in a straight line, right? Think of a sunbeam cutting through a dusty room. It reflects off a mirror, just like a little ball bouncing off a wall. This idea was so simple and elegant that it was basically the law for over 100 years. I mean, who's going to argue with Newton? But then, in 1801, this physician and physicist named Thomas Young came along, and he designed an experiment so clever, so powerful, that it just completely blew Newton's particle theory right out of the water and changed science forever. So to really get what Young did, let's just imagine something simple first. Say you're firing tiny particles, think of it like sand, at a wall with two little openings in it. What do you get on the screen behind it? Well, exactly what you'd think. Two distinct piles of sand right behind the slits. Super simple, totally predictable. Okay, but what if we do the same thing with waves, like ripples in water? When the waves pass through the two slits, they spread out and start to interact with each other. Where two wave crests meet, they get bigger. Where a crest meets a trough, they cancel each other out. So you don't get two lines. You get this weird striped pattern of high and low points. This is called an interference pattern, and it's the unique calling card of a wave. Right, so here's the billion-dollar question. What did Thomas Young see when he did this with a beam of light? Did he see two lines, like Newton's particles would make? Nope. He saw the striped interference pattern. The conclusion was just staring him in the face. Light was not a particle. Light had to be a wave. And for the entire scientific community, that was pretty much it. Case closed. The evidence was right there. You couldn't deny it. Young's experiment was so clear that for the next 100 years, the wave theory of light was king. The debate was finally over, or so everyone thought. Let's jump forward now to 1905. A young patent clerk you might have heard of, Albert Einstein, was looking at this odd little phenomenon called the photoelectric effect. It's basically how light can knock electrons loose from a piece of metal. And he realized something. The wave theory of light just couldn't explain it at all. I mean, look at this timeline. It just perfectly shows the scientific whiplash that was going on. 1704, Newton says particles. 1801, Young comes along and proves it's waves. And then, in 1905, Einstein shows that to knock an electron off a piece of metal, light had to behave like a tiny, discrete bullet of energy. He proved light had to also be a particle. He literally brought Newton's old idea back from the dead. Einstein called these little energy bullets photons. A photon was a single particle, a quantum of light. But here's the catch. It also had wave properties, like frequency, which is what gives light its color. So, light was now officially a paradox. It was somehow, impossibly, both a wave and a particle at the same time. And just when you thought it couldn't get any weirder, it did. Scientists figured, okay, let's try the double-slit experiment with something we know is a particle, like an electron. And what happened? You guessed it. They got the same wave interference pattern. This wave-particle duality wasn't just some quirk of light. It looked like it was a fundamental rule for everything. Okay, this is where the story goes from just being a paradox to being profoundly, deeply strange. To figure out what in the world was going on, physicists took that double-slit experiment to its absolute extreme, and they stumbled upon one of the most bizarre truths about how our universe works. So they asked this: what if we just slow things way down? Let's just fire one single electron at a time. I mean, there's no other electron for it to interfere with, so surely now we're just going to get two simple lines, right? The particle has to pick one slit or the other. It's only logical. But that is not what happened. Each electron would land on the screen as a single, tiny dot, just like a particle should. But, and this is the part that will bake your noodle, as they sent them through, one by one by one, those individual dots slowly built up to form the wave interference pattern. It's as if each electron, all by itself, went through both slits at the same time, interfered with itself, and then landed in just the right spot to help make the pattern. How is that possible? Well, to try and explain this madness, physicists like Niels Bohr and Werner Heisenberg came up with something called the Copenhagen interpretation. They said that before you look at it, a particle doesn't really exist in any one place. It exists as a wave function, which is just a wave of pure probability, a cloud of all the places it could be. And that probability wave is what goes through both slits and interferes with itself. And here is the absolute craziest part. When scientists put a little detector by the slits to see which one the electron actually went through, the weirdness just stopped. The instant the electron was observed, the interference pattern vanished, and they were just left with two simple lines, just like the sand we talked about earlier. The very act of looking at it, of measuring it, forced that wave of possibilities to collapse into one single reality. It seems that reality literally changes depending on whether or not we're looking at it. So for decades, this observer effect was this baffling, almost mystical conclusion. But today, our most powerful theory of physics, quantum field theory, gives us a different and maybe more elegant way to think about all this. It basically says that the original question, is it a wave or a particle, was the wrong question to be asking in the first place. See, quantum field theory says that the most fundamental thing in the universe isn't a particle or a wave. It's fields, invisible, energetic fields that stretch across all of space and time. So what we think of as a particle, like an electron, isn't a little ball at all. It's just a tiny, concentrated vibration, a little ripple in a huge, universe-spanning electron field. And a photon of light? Well, that's just a ripple in the electromagnetic field. From this point of view, particles and waves are just two different ways that these field vibrations appear to us. The field itself can act like a wave, which explains the interference pattern. But the vibrations in that field come in discrete, countable packets, which is why they also act like particles. It's not one or the other, it's both, because they're just aspects of the same underlying thing. And that kind of brings us to a final, absolutely staggering thought. If the fundamental reality of our universe isn't solid little objects, but just ripples in these invisible connected fields, what does that even mean? If the chair you're sitting in, the screen you're looking at, even your own body are all just a really complex dance of vibrating fields, what is the world really made of? And that's a question maybe even bigger than the one we started with.